All right, yet another unclear aspect to one of these problems. I did not indicate that this was a frictionless situation, but it was my intent to do so. Since friction's not mentioned, I don't think it's always okay to figure that it's not, but we will say that the kinetic friction, and we'll call it K, is equal to 0. That's kinetic energy. Let's not use K. We'll just say small f for friction is equal to 0. Okay? All right, if we know that that's true, then a free body diagram of the forces acting on the block. Start with the simplest. We have mg, it's weight, acting downward. We have the force acting at a downward angle of 27 degrees. I'll just write it as theta. And F is acting down that way. And then we have the normal force acting upward. And those are all the forces that are indicated. Now this was a little bit different because we were not told that it was moving at a constant velocity. We were in fact given the parameter acceleration is equal to 1.5 meters per second. Okay? As you can see, it is going to be this x component of the applied force right here, Fx, that's going to do that accelerating, because we will have a y component, Fy, acting down this way, right? That sort of gets rid of our F over here, right? So that's what it would look like. This right here is what our free body would look like if we replaced F with its components. Of course, we don't really do that, but you know what I mean. All right, so of course the normal force would have to be equal to the combined sizes of the gravity vector and the normal force vector. So why don't I just redraw that in a way that is compliant with that requirement. All right, so N acting upward, we'll get rid of that one, and then we'll just move these other two vectors down where they belong. Mg, weight vector acting downward, and the y component of the force vector. Okay, so that tells us how big N should be. So throwing these out over here, here's our appropriately drawn free body diagram. All right, moving on a little bit, the magnitude of force F. How are we going to figure out what that is? Well, let's start with our two-equation strategy. We know that the net force in the x direction is equal to ma in the x direction, the x acceleration. We are making the assumption that the net force in the y direction is 0, right? If it's accelerating along this plane right here, we know that the forces are balanced in that direction. Okay? So coming back down here, this is our assumption right here. Fy is equal to 0. So now working with Fx, the net force in the x direction equal to ma, or the acceleration, the mass times the x component of the acceleration. All right, so taking a look at that, what else do we have acting in the x direction? As I said a second ago, all we have is this component right here, the x component of the applied force vector. All right, so that is our net force. So if we come down here, we could say net force in the x direction is just equal to Fx, the x component of our applied force. Setting those equal to each other, we know that Fx is equal to max. All right, so how's that going to help us? Well, if we know the angle at which this force acts, here's Fx here, we have it already, and here's F right here, the applied force, and here's our angle theta, then we can figure out what the magnitude of the x component is in terms of theta and the force, and that way we can just figure out what the total force is. All right? So Fx, how does Fx relate to F? Well, if we draw a triangle right here, and then pull it over, we know that the length of this side is Fx. We know that the length of this side is F. We know that this angle is theta. So we are dealing with an adjacent leg and the hypotenuse. So we know that the cosine, of theta, because it's adjacent, is equal to the adjacent leg, Fx, over the hypotenuse, which is the entire magnitude of F. So that tells us that F is going to be equal to Fx over cosine theta. All right, well, how does that help us? Well, let's move this down out of the way here. Oh, that did not work. All right, let's just come down over here to the side. And we will say that if F is equal to Fx over cosine theta, and Fx is equal to the mass times the x acceleration, then we can say right here that F is equal to Fx max, I'll do it in blue so it corresponds to what we did over on the left-hand side, divided by cosine of theta. All right, we know the mass, 9 kilograms. We know the acceleration, 1.5 meters per second squared. We know the angle theta, so we have everything we need. F is going to be equal to 9 kilograms times 1.5 meters per second squared, divided by the cosine of 27 degrees. All right, now just plugging all that into our calculator, we get that the force is equal to 15.15 or 15.2 newtons. So that is the magnitude of this applied force that's heading down the building. Okay? So now part C, I'll do in a different recording.